welcome to the 36th lecture of this course. Today we will talk about this important theorem known as Rice's theorem in the context of undecidability. So, Rice's theorem gives us a mechanism to show the undecidability of an infinite set of languages. Okay. So, it shows that if a language has a certain form, then we can prove that it is undecidable. So, in that sense it is a very powerful theorem, and what we are going to show today is we will first see the statement of Rice's theorem, and then we will look at a proof of the correctness of the statement. Okay. So, before I state Rice's theorem, I need to introduce a few definitions. So, the first thing that we will see is a property of languages. Okay. So, a property of languages is a function p that goes from the set of all languages to 0 1. Okay. So, basically we associate with every language either 0 or 1. Okay. So, what that means is that, so if we associate 1, we say that the language satisfies the property P, and if we associate 0, we say the language does not satisfy P. Okay. So, for a language L, if P of L is 1, we say that L satisfies P, and if P of L is 0, we say that L does not satisfy the property P. Okay. So, this is what we mean by property of languages. So, some examples. So, you can construct any example for a let us say that so examples of properties. Okay. So, the language, so I will just use L for language. Okay. So, L has the string 0 1 1 0. So, there are some languages which will have that string, there are some languages which will not have that string. Okay. So, this is a property. So, such that languages which have this string, we will say that those languages satisfy this property, others do not satisfy this property. Okay. The L is empty. Okay. So, basically this means that languages which are empty, for them we say that in fact there is only one empty language. So, that is the only language which satisfies this property, all other languages will not satisfy this property. Okay. L has 1000 strings. Okay. Once again there are a finite number of languages which have so many strings. Other languages have either less or more number of strings, and so on. So, you can have lots and lots of properties. Okay. So, now we defined what is called a non-trivial property of languages of Turing machines. So, P is said to be a non-trivial property of languages of Turing machines if there exists Turing machines M1 and M2 such that P of L of M1 is 1 and P of L of M2 is 0. Okay. So, we say that a property is a non-trivial property of languages of Turing machine if there is some Turing machine whose language satisfies that property and there is some Turing machine whose language does not satisfy that property. Okay. For example, if I say that if I look at all of these properties, okay, so there are Turing machines whose language is empty, there are Turing machines whose language is not empty. There are Turing machines whose language has 1000 strings, we can construct. There are Turing machines whose language has more than 1000 or less than 1000 strings. Similarly for the first property also. So, all these three properties are non-trivial properties of languages of Turing machines. Okay. So, now we can state Rice's theorem as follows. Let P be a non-trivial property of languages of Turing machines, then the language consisting of those Turing machines, so I will call it L subscript P, okay, encodings of machines M such that L of M satisfies P, or I can write it as P of L of M is equal to 1 is undecidable. Okay. So, if we have a non-trivial property of languages of Turing machines, then the language of encodings of Turing machines whose language satisfies the property is undecidable, okay, which also means that the language of encodings of machines whose language does not satisfy the property is also undecidable, because decidable problems are closed under complement. Okay. So, what it means is that, so we had actually already proven for this. Okay. So, remember that the language ETM that we had shown consisted of encodings of all those machines whose language was empty. Okay. So, that is basically one way to show that. So, this, so if we prove Rice's theorem, it gives us an alternate proof of the fact that ETM is undecidable. Okay. So, how do we prove this property? How do we prove the theorem? So, we will prove the theorem in two parts, in two cases. So, case 1, okay. So, consider the language phi, okay, that is the empty language. Okay. So, case 1 is, so assume that, so we have this property P, assume that P of phi is 0. Okay. So, if we assume that P of phi is 0, then what we can say is that since P is a non-trivial property of languages of Turing machines, okay, there exists a Turing machine, okay, such that the language of, so there exists a Turing machine, let us call it N, such that the language of N satisfies the property, or in other words, P of L of N equals 1. Okay. So, here we have a language which does not satisfy the property. So, that means that there must be some other Turing machine whose language satisfies, and of course, we can construct a Turing machine whose language is empty set. Okay. So, we just have a Turing machine which rejects all inputs. So, we of course have a Turing machine for phi. Okay. So, now, so using this Turing machine, we will prove that, so using this, we will show that ATM reduces to LP. Okay. So, recall that ATM is undecidable. So, this will prove that LP is undecidable. So, what is the reduction? So, the reduction, let us call it F. So, what will F do? So, F is a function, okay, which will take an instance of ATM and it will produce an instance of LP. Okay. So, what F does is that it takes, let us say, an instance of ATM M comma W, and it will produce, okay, an instance, let us say, M prime. Okay. So, we have to design M prime given M comma W. Okay. So, this is what we have to do. So, we take as input M comma W, okay, and then we give a construction of M. Okay. So, design a Turing machine M prime that on any input x does the following. Okay. So, before I give the description of M prime, let me say something. So, we just saw that there exists a Turing machine N whose language satisfies the property. Okay. So, we saw this existence and we said that this Turing machine, we called it as N. So, what we will assume here is that the Turing machine M prime that we are going to design has a copy of N hard coded into its description. Okay. Of course, it has M W also, but it also has this Turing machine N hard coded. So, let me write it. So, M prime has a description of n hard coded into its description, together with, of course, m and w. Okay. So, once again, so how should you picture this? I mean, picture this as, so you want to write a program m prime, okay, or you want to write and design an algorithm m prime. So, this algorithm, what it does is that, so inside the description of the algorithm or inside the description of the program, there is already a description of n, m and w that is given in the description. Okay. It is not part of the input, it is part of the description of this program. Now what it does is that, now given any input x to m prime, now we have to decide how will the Turing machine m prime behave on x. Okay. So let us, so I want to emphasize this fact because this is very important, that all these three things n, m and w, they are not part of the input. Okay. In other words, they do not change with different inputs. So x is what is the input. Okay. So x is what will change every time you run the program, or it might change, but these three things, they remain constant for every, so every time you run the machine m prime. So, first m prime, it will simulate m on w if m rejects w, then it rejects, okay, it does not do anything. If m accepts w, then simulate n on x. Okay. So, if the machine m accepts w, so here there are two things that can happen, in fact three things. If m rejects w, then we reject. If m runs forever on w, then of course it runs forever, it never goes to the second step. But if m accepts w, then what we do is that we take the description of the machine n and we simulate the input to m prime on the machine n. Okay. Now, if n accepts, then accept, and if n rejects, then of course reject. Okay. So, our machine m prime, it is rejecting here once. So, if n rejects, it will reject, and if m rejects, then also it rejects. The only time it accepts a string, if m accepts w, okay, and n accepts x. Okay, so, let me write it here explicitly. So, if n accepts x, then we accept. So, now, so that is all. So, this is the description of the machine, and now once we have this description, we just output the description of m prime. Okay. So, now let us see why this reduction is correct. So, suppose if m accepts w. So, what happens in this case? So, if m accepts w, then what we have is that m comma w is a yes instance of ATM. Okay. So, it means that mw is accepted by a machine that accepts ATM. So, if m accepts w, then what we have here is that we simulate n on x, then if n accepts x, then we go ahead and accept x. Okay. So, then the language of m prime is going to be all those strings that are accepted by the machine n, okay, is nothing but the language of n. So, whenever n accepts an x, m prime will accept the same x, which implies that, okay. So, the language of m prime is the language of n, and we know that. So, again from our assumption, we know that the language of n satisfies the property, it satisfies the property p. So, therefore, p of L of n is equal to 1. On the other hand, if m does not accept w, then we do not even go to the next step. Okay. So, we do not even go to the third step here. Okay. So, we directly reject. So, in that case, the language of m prime is equal to phi, okay, and our assumption was that p of phi is 0, which implies that p of L of m prime is 0. Okay. So, here actually what I should say is that, so since the language of m prime and the language of n are the same, so therefore, p of L of instead of n, I can write this as m prime also is equal to 1. Okay. So, what we have here is that if m accepts w, then p of L of m prime is 1, or the language of m prime satisfies p, and if m does not accept w, then the language of m prime does not satisfy p. Okay. So, therefore, ATM reduces to the language of p. Okay. So, this is the first part of the proof. Okay. So, remember that we had only considered the case when p of phi was equal to 0. Okay. So, now we need to consider the case when p of phi is equal to 1. Okay. But actually this case is not very different. In fact, what we will do is we will reduce this case to the case that we just saw. So, suppose if p of phi is equal to 1, so this is case 2. So, we will reduce this to case 1. Okay. So, if p of phi is equal to 1, consider the complement property. Okay. So, consider the complement property p bar. Okay. So, what is p bar? So, whenever p of a language is equal to 1, p bar of that language will be 0, and whenever p of a language is equal to 0, p bar of that language is equal to 1. Okay. So, it basically just assigns the other bit, the complement bit. Okay. So, I mean if you want, you can define it also. So, p bar of a language L is equal to 1 minus p of L. Okay. So, if p of L is 0, then p bar of L is 1, and if p of L is 1, then p bar of L is 0. Okay. So, now since p phi is equal to 1, therefore, p bar of phi is equal to 0. Now, whatever we said for in case 1 for p of phi, we can say it for p bar of phi. Okay. So, therefore, by case 1, what we have is that ATM reduces to L of p bar. Okay. So, this is by case 1. Now, let us understand what is happening here. Okay. So, if ATM reduces to L of p bar, then what I can say is that ATM bar reduces to L of p bar whole bar. Okay. So, this actually again follows from the definition of reduction. Okay. So, remember, so recall the definition of reduction. So, how did we define? So, we said that a language L reduces to a language L prime if for all x that belongs to L is mapped to L prime and every x that does not belong to L, that is which belongs to L complement, is mapped to L prime complement. Okay. So, that is all that we are using here. So, if ATM reduces to L p bar, then ATM bar reduces to L bar of p bar. Okay. So, I mean the general statement is that if A reduces to B, then A bar reduces to B bar. Okay. Now, what is this language L bar p bar? Okay. So, before I state, so observe that L bar of p bar, how do we define? So, it is set of all those machines M. Okay. So, L of p bar is all those machines M which does not satisfy P. So, L bar of p bar will be all those, will be the complement of that language. Okay. So, therefore, it will be all those machines M such that L of M, or just to add one more step. So, it is complement of the language such that L of M does not satisfy P, okay, with a bar on top, which is nothing but all those machines M which satisfy P. Okay. Therefore, ATM bar reduces to LP. Okay. So, in case 1 we had shown that if P of phi is equal to 0, then ATM reduces to LP, and in case 2 what we showed is that ATM bar reduces to LP. Okay. So, both ATM and ATM bar are undecidable problems, therefore, LP is undecidable. Okay. So, that completes the proof of Rice's theorem. Okay. So, a few quick applications. So, for example, if we consider language of machines M such that let us say L of M is finite. So, there are machines whose languages are finite, there are machines whose language is not finite. So, this is undecidable. Instead of finite, now we can have let us say regular, which we have already shown. Okay. Language of machine which contains the empty string, okay, so which contains epsilon. Okay. So, all these, so you can construct an infinite set of languages which are undecidable. Okay. So, all these problems will be undecidable by just applying Rice's theorem. Okay, so I will stop here today. Thank you.